The last class, we spent time in trying to understand the CW operation of a CO2 laser. We also tried to see how we can increase the power that can be obtained from a CW CO2 laser. And we saw that methods are like increasing the active length of the discharge tube. We found that there are some limitations to it. Then fast axial flow laser, where the gas mixture is flown at a very fast rate from one end to the other in the discharge tube. And the catalytic requirement of catalytic reconverter, which actually converts back the dissociated CO and oxygen back into CO2. We also saw the transverse CW CO2 laser, and we found that the maximum power that can be obtained from such CO2 lasers can go up to almost kilowatts CW, which is very good. It is used for cutting, etc., and has many other applications. But there are also certain applications where you want to increase the output power obtained to peak powers of megawatt or so. In that case, we also went very briefly some time on it as saying that we can increase the uh, active molecular density, that is increasing the pressure. But we also saw that by increasing the pressure, the glow to arc transition time also reduces. That means it is very difficult to maintain a glow discharge, and therefore it is not possible to have a CW kind of operation, and one has to go for pulsed operation of a CO2 laser. So we come to the pulsed operation of a CO2 laser. And here, when we talk of high pressure, I'm generally meaning atmospheric pressure because that is a very common mode of operation of a CO2 laser. And therefore, we come to the pulsed operation of a CO2 laser where the pressure that is maintained inside the discharge volume is atmospheric pressure. And the ratio of the gases, I will tell later, but you can assume it is about 1:1:10, where CO2 and nitrogen are in equal proportion, and helium is 10 times that of this. Okay, so for the pulsed operation of a CO2 laser, the first thing is you require a pulsar circuit. So what is a pulsar circuit? As it is shown here, you can see here, this is the pulsar circuit. So the pulsar circuit, what we try to do is you try to store large amount of energy in the capacitor. Okay, you try to store a large amount of energy in the capacitor and make it discharge through a switch into the laser. And this discharge is so fast. So fast, how much fast you want? You want that the discharge current should flow through the laser load within the glow to arc transition time. So this is the requirement. So when such a large amount of energy which is stored in the condenser is switched into the laser load, it creates a glow discharge. And because the peak currents can be very large, the excitation is also very high, and therefore the gain that is created, the population inversion that is created is also very large. And when you have stimulated emission, bringing down that entire population down, your peak powers can go into megawatts. So how it happens, just let us try to understand this circuit a little. You might be already, I do not know if you have come across such a circuit, maybe in case of Excimer laser or other gas lasers, which you might have studied. But we will just go through it very, very briefly. So basically what you have is you have a high voltage supply, right? This is a high voltage supply, which is say V0, and you charge a condenser through this. This is the charging bypass, which is grounded. So this is R and this is R. What is the requirement of this R? I will just tell you in a moment's time. So your condenser is getting charged through a resistance. We know how a condenser gets charged. We know that the voltage across the capacitor or the condenser will go as V naught into 1 minus e raised to minus t by RC, where V naught is the charging voltage. So at time t is equal to infinity, Vc is equal to V0 at equal infinity, and Rc is the time constant. So in this time constant, it rises to about 0.7 times that of V0. So the condenser gets charged, and when it gets charged to the required voltage, we actually have a switch, which is nothing but a spark gap, basically two electrodes, and the separation between these gaps is so arranged, so adjusted, that it is the voltage that you want the laser to switch it. And so this condenser then switches through a laser load. I'm just showing the laser load as again two electrodes. So once this is charged to the required voltage, it switches, the switch closes. When the switch closes, the condenser sends the energy that is stored in it in the form of current through this conducting switch into the laser load, right? So you have the discharge of the condenser into the laser load, creating this current. And how would you, this discharge duration, on what does it depend? It depends, of course, on the value of this capacitor. It also depends on the impedance in this circuit. So impedance of the circuit has to be properly adjusted so that your discharge duration is less than the glow to arc transition time, which is few hundreds of nanoseconds at atmospheric pressure. So we ensure that our discharge duration, so we see that our capacitance value, the associated inductance, the resistance. Of course, the laser load also has its own impedance associated with it. So in addition to it, whatever we have here, it is such that our discharge duration is maintained within the glow to arc transition time. Now, once the condenser discharges into the load, we have gas mixture, which is in the interelectrode volume, that gets energized. Now, why am I showing our electrodes in this manner? See, before that we had our CW discharge. It was something like this. It was longitudinal, and we said it is about 1 meter length is a very commonly used discharge length. But you see, maintaining a longitudinal glow discharge at high pressure enclosing appreciable volume calls for extraordinarily high voltages. If we think of, say, 1 centimeter gap, okay, and if we want to create if you want to break this gap, then you require approximately about 25 kV per centimeter. So we cannot think of such large discharge lengths. But so then, because we cannot have longitudinal discharge, what we have is a transverse discharge. So I show here the electrodes. So this is one electrode, upper electrode, and this is the lower electrode. The upper and lower electrode are facing each other. So this distance could be about 8-9 mm or at most 1 centimeter. This width is also about that much, 0.8 to 1 centimeter. This is 0.8 to 1 centimeter. And this is extending. This length could be about 40 centimeters or more, depending on what kind of output we want from this laser. So now what we have is, you have two electrodes facing each other, enclosing a volume in which your laser gas mixture is filled, and it extends over a length. And your this point A is connected to the upper electrode, and your this point is connected to the lower electrode. Right? So these are your longitudinal electrodes which are facing each other, and the discharge is a transverse discharge. And therefore, this kind of operation is called transverse operation. And if it is at atmospheric pressure, such laser is called transverse TEA laser, transverse electric atmospheric CO2 laser. So normally these TA operation, T lasers are very common in CO2 because maintaining at atmospheric pressure is simpler as compared to high pressure or low pressure. So TEA CO2 lasers are very common. Now, so now we have understood that we do not have longitudinal discharge here, but transverse discharge between electrodes which are facing each other, enclosing a volume between them in which we have our lasing gas mixture and in which we are creating the glow discharge. Now, these electrodes, we are always worried about instabilities. Why we say that you cannot have glow discharge? Because if there are instabilities, they do not diffuse out, and if they do not diffuse out, then there can be a arc discharge. Now, wherever you have very strong curves, edges, there the field becomes very large. This is called the edge effect. Therefore, if you have very strong edges, then instead of glow, you can actually have arc between these points. And that is simply not what we want. Because if you have arc, then your entire energy that you have stored in the condenser will just go through the arc regions. So in the volume will be too small to have any appreciable output. So to avoid that, one normally makes use of contoured electrodes or profiled electrodes. Yes, there is an enhancement in field. That does not happen. And there is a uniform field distribution in the entire active region. However, in spite of uh, profiling our electrodes, in spite of making our discharge duration within that glow to arc transition time, yet it is very difficult to get a uniform glow discharge in that large volume. We definitely require some appreciable volume because that is what will give us the total energy output. So in that entire volume, getting the kind of glow discharge that we require of uniformity is difficult. And therefore, and what is the reason for this? Once again, the reason is the presence of instabilities. Instabilities in the form of pockets of regions where you have the number density of electrons, initial stray electron density. Normally, the stray electron density is something like 10 to the power of 3 or so per cc. So that is more in some places, less in some places. And because of this, and because we also have at high pressure, the mean free path is small, so these cannot diffuse out, and therefore there is a possibility of arc formation. So to avoid that, what happens is that what is done is that we create small arc discharges along the length. How are these arc discharges created? Once again, basically you have charge a condenser, C, which is made to discharge once again through various pins that are ballasted by resistances. We have a switch. So the condenser that is charged is made to, this is the switch, spark gap. When we want, the condenser basically discharges through these number of spark channels which are placed along the length. So what happens, as you see here, these are the spark channels which are placed along the length of the discharge. So when you have sparks between these pins, along with the spark, what do you mean by spark? You also see light in it. In that light, along with visible light, there are also some UV radiation. So this UV radiation actually goes into the interelectrode region and it causes further ionization. So this ionization brings the stray electron density, which was 10 to the power of 3 per cc, say, it is increased to maybe 10 to the power of 7 per cc or so. And so the initial number density of electrons becomes higher, And therefore, any small variation in it here and there doesn't really matter. And when we discharge the main condenser through the switch into the laser load, it results in a good uniform glow discharge. So this is how one creates a uniform glow discharge. And once you have glow discharge, then what happens? Then you have the excitation of the species, CO2 as well as nitrogen. Nitrogen transfers its excitation to CO2 molecules. You have population inversion created. And once you have population inversion, then if you have proper resonator cavity in place, then you can have an output. So this is a typical look of a transversely excited atmospheric CO2 laser, EVA CO2 laser. See, these are the electrodes that I was mentioning. Can you make out that they are actually electrodes with some dimension, and they are placed facing each other, and the pulsar circuit, that is this part and this part, are connected to the capacitor through the switch, so that the capacitor discharges into this. And these are the pins, pre-ionization pins, which are placed all along the length of CO2 laser at regular gaps, so that the UV photons that are emanating from the sparks when these fire into the intermediate gap, they can cause the pre-ionization, and they ensure that there is no arc but a good glow discharge when the capacitor discharges into the laser. I had told before that gas composition is something like this. CO2 and to helium is 1:1:10. Whereas for CW operation, continuous wave operation, we have always said it is 1:1:4, 1:1:5 is good enough. So why so much higher concentration of helium here? That is because helium here has two roles. First is, of course, repopulating the 010 level. We know that the 100 and 020, they come down eventually to 010, and they have to be brought down to the ground through collisions with helium, VT relaxation. And so for that, we definitely require helium. And now at higher pressure, we also require large amount of helium to bring this down effectively. That is one. But the second rule, and which is also very important here, is that helium is a very noble gas. It has no electron attachment, electron affinity, and therefore the electrons which are created in the discharge, they are not lost because of attachment to oxygen or CO. They are not lost. They undergo their collisions with helium, and therefore they are present in the discharge. They continue to sustain, they continue to excite. In case the formation of negative ions takes place, we know that mobility of negative ions is very short. And again, that can also lead to instabilities, and it can create. So the role of helium is to ensure that the glow discharge condition, the electron number density inside is properly maintained. This is called E by N, that is the number of electrons to the neutral species. So this ratio is properly maintained as is required, and one has a good glow discharge. One more thing that we have to keep in mind is that here, as you can see, peak current that can go through the discharge. See, this is the laser. Okay. So this is the capacitor, and we are charging it. When I said when the gap is about 1 centimeter, you require about 25 to 30 kV. So suppose this is 30 kV. The resistance encountered in a glow discharge is not more than a few tens of ohms. Suppose it is 10 ohm. Then you can see that the peak current that would flow is almost how much? 3 kiloamperes, right? So such large current flows through this, and therefore the dissociation of CO2 into CO and oxygen is also high, and therefore the presence of helium is very, very important so that the negative ion attachment doesn't happen. Most of the collisions of the electrons are with helium, and therefore we have a very large concentration of helium here, right? So now now let us see how the temporal profile of lasing looks like. Now, as the capacitor discharges, we know that low discharge is established, population inversion is created. So this is the discharge profile of the capacitor discharging into the laser loop, right? So this is the discharge current. We just now saw that this peak current can be kiloamperes, and the duration of discharge is, we do not want it to exceed a microsecond. Definitely, it is a few hundreds of nanoseconds. Now, when the gain exceeds, so now the population inversion is getting created. When the gain exceeds loss, that is when stimulated emission can set in. How stimulated emission sets in? It sets in from noise. So there is some spontaneous noise. That spontaneous noise, which is along the axis, that will cause more stimulated emission, and then stimulated emission slowly will set in. Now, during this time, when the stimulated emission is setting in, the gain continues to rise because the gain is not being leached, so the gain continues to rise. And when stimulated emission is finally set, then this population inversion which is there, which has been created, that is quickly brought down through stimulated emission. And this is seen as the output power. You can see there is a peak in the output power, which is followed by a tail. So this is called gain switched peak. Why is it called gain switched peak? Because the lasing is switched by the gain in the population inversion. The gain as the difference between CW laser, in the CW laser, basically, as you can see that this is the gain, and if suppose this is the loss line. So the gain continues to rise, and as it crosses the loss line, that is where your stimulated emission tries to set in. And when it sets in, then the gain is brought back to the loss line because the gain is getting consumed. So it is brought back to the loss line. And when it further goes down, then the gain becomes less, then it again goes up. So eventually these are the transient, and it gets locked to the loss line. This is called latching. I think you must have studied this in your previous classes. But now in case of this pulsed laser, what is happening is that the gain is rising very fast because our current is very large as compared to your CW. So the gain is rising very fast. It has reached the loss line here. But before the stimulated emission can set in, it further rises. So when the stimulated emission now is set and it has to leach the population from the upper level to the lower level through stimulated emission, you can see that there is so much of gain above loss. And therefore, this is realized as a very sharp, high peak output. That is seen here. And once it comes down to once the gain comes down, then it again comes close to the loss line, and then it eventually falls when your inversion is killed, because our excitation pulse is long gone. And there is one more thing that you have to mind is that there is a definite gap of about 600 to 800 nanoseconds. It depends from system to system. This delay is the time it takes for the gain to build up. Once the gain has built up, that is when you have the output power. And this tail that is very, very conspicuous of a CO2 laser discharge is due to the presence of nitrogen atoms. We know that nitrogen, it stores energy, and it is eventually delivering it to CO2 through collisions. So even when the direct excitation of CO2 is long over, the gain in nitrogen remains and it continuously is fed to CO2. And this is seen as the output power, which comes even after the gain switched peak. So this gain switched peak is, we can consider it as generally constituting of the population inversion, which is directly given to CO2 molecules in the excitation during the current pulse. And also, of course, there is some collision with nitrogen which is adding to it, but primarily because of the active species, and the tail is contributed largely by nitrogen. So if we want to have a less gain switch spike and large duration of the pulse, then you can increase the concentration of nitrogen. And on the other hand, if you do not want much longer tail, then we can actually try and reduce nitrogen concentration so that our pulse duration becomes smaller. So it typically you can get about few joules of energy from a conventional CO2 laser. You can go up to 2 joules, 3 joules are very commonly obtained. And therefore, you can say that the peak, and if you just consider the gain switch spike, which is about 200 nanoseconds, you can get as large as maybe 10 megawatt peak power. And this megawatt of peak power, and as I'm saying, few joule, maybe 2 joule energy, this is obtained over a pulse, over a beam of diameter. As I said, you can take it as 1 centimeter by 1 centimeter. So this can be further focused, and the intensities that can be obtained can be very, very large. And such high intensity pulsed output from a CO2 laser is put to many, many uses. For example, when you want to drill, when you want to weld, when you want to such drilling, what are the other applications? Manufacturing industry, most of the applications do make use of such high intensity, high peak power, short duration TaCO2 laser. Now, we have seen pulsed operation, and we have seen how the temporal pulse of a laser looks like. Temporal is in time, so how it looks in case of a laser. But we also want that the average power that is obtained from the laser increases. It is not enough to have one pulse, you have 5 joule, and then the second pulse comes after many, many seconds. Maybe many a times you require a continued operation, that is repetitive operation. So one also needs to be able to operate this laser in repetitive mode. So that is what we will try to take up next time. So today what we have learned is we have tried to understand the pulsar for a laser. The pulsar consists of a energy storage capacitor which is charged using through a resistance from a high voltage DC power supply, and it is switched through a spark gap, right? And this spark gap, because the peak the voltage is very high, kilovolts, the peak currents are also very high, and therefore this spark gap is able to take care of this high voltage, high current, and we are also able to get a very short discharge, which is required for obtaining a glow discharge and not an arc discharge at that pressures. And we have also seen that how pre-ionization is really required. These are called pre-ionizer pins, as I had shown you. These are kept all along the length, and why these pre-ionization pins are required to precondition the active volume. So we'll take up next time from here.